And there we go. Now we're live. So welcome back. This is going to be a almost entirely coding video. I haven't even started Kerbal Space Program at this point. What I wanted to do was to quickly go over the hill climbing and node execution code, which I imported from CheersKevin. I have on the screen his code that I imported from, which is from his episode 39 of his Kerbal Space Programming series. He has made that available on GitHub. I include a link to it in my code that I copied from him. And I made some changes to make it fit within the paradigm I wanted to use, and we'll see how that works shortly. I also made some changes to pander to the VS Code block hide. So for instance, if I have a function here, let's say I want to hide this abort block, notice that when I say fold it, it folds the whole thing. I've mentioned this before. If the close brace were on the next line, then the folding would do that. What I wanted to be able to do is fold a whole bunch of blocks and have them on one line each. And I prefer this style with the close brace on its own line and extended to match. I'm an old C programmer, and that's how I learned to do it from K&R back in the late 70s. So that's how I prefer to do it now. But if we pulled it up like this, we can fold our blocks together, and we end up with one line per folded thing, and it gets them out of the way and makes it easier for us to work with. So what is it this does? This is a library. It has a global symbol it provides called HILLCLIMB. And this means that anybody who imports this file, runs this file, will end up with a symbol HILLCLIMB. It'll be the only thing this does to your global namespace. And HILLCLIMB will be a lexicon where you can pick up various methods. This is a library mechanism that Kevin used in his KS programming series, and it's similar to what I was doing. I have gone back and forth on import and export strategies, all the way from one side being you run a file and it defines all of its functions globally, which is what I'm using right now as an experiment. The other extreme I actually prefer from an engineering standpoint, but it's more awkward in Kerbal Space Program, where you import a library and it makes no changes to the global namespace. Instead, import and export themselves manage a local variable which has a lexicon. You say, well, I'm going to import HILLCLIMB, and it would give you back an object which you can assign to a local variable, whatever name you want. Downside of that is everybody that uses HILLCLIMB has to import it. Upside is everybody who uses HILLCLIMB has to import it. So anyway, so what Kevin settled on here was kind of a happy medium where each module that you import adds one thing to the global namespace, which is itself. So you wouldn't have two libraries called HILLCLIMB because there'd be no way to pick which one. You would run one script or the other, and they would both overwrite the single global variable. So what does it do? Well, the main entry point is to do a HILLCLIMB. I have a co-pilot down here who's getting, you want to be picked up, huh? You want to say hi? She's my coding partner. She saw I was online and she said, I want to be part of this. And now she's saying, but I don't want to be part of this. So she just wanted to say hi. Anyway, so the primary purpose of this is I want to HILLCLIMB. I have a data vector of some sort here on both sides. And I have a fitness function. And I have a step size. And the purpose of HILLCLIMB is to tweak the data vector, to perturb the data vector in each of its dimensions by the step size repeatedly until you find a modification to the data vector which best maximizes the value of the fitness function. So what is the seek logic? We have a default step size, which we can provide. I don't use that because the step size is going to be changing from problem to problem. So the basic logic, which is common between these two, is find your best neighbor, and if the best neighbor isn't better than your current data, you're done. If it is, then step to that best neighbor and repeat. So we repeatedly say, find my best neighbor in some global sense of what best is, and step to it, and then find the neighbor and step to it, find the neighbor and step to it. Now, the engineer optimizer in me is looking at this saying, oh, we're calling the fitness function inside best neighbor to find the best neighbor, and then we're going to call it again out here, and then we're going to call it again for us. And as we step around, one of the neighbors is going to be the old us. And the realist in me is saying, if the fitness function is that expensive, then the fitness function should be responsible for memoizing the fitness for a given vector and saying, oh, I recently computed the fitness of this vector, I can return it immediately. So I agree with Kevin here in that this is not something that the seek function needs to worry about. So we're not going to cruft up our seek with somehow remembering fitness values for vectors. We're just going to do the real simple thing. Keep it simple. After 40 years as a software engineer, I am still learning things. So admittedly, when I saw Kevin doing this, I had 35 years in the business, and I said, oh, yeah, he's keeping that nice and simple, and that's something I need to learn from. I always over-engineer, always. So the changes you'll see me make on the right-hand side, often I will be over-engineering things, and I'm sorry, and that's just the way I am. I can't not do this. So there we go. Same logic on both sides. He writes it a little bit differently. I had a hard time with the fact that he's calling best neighbor in two different lines, so I kind of twisted the loop around, and then I said, well, if somebody pulls the abort switch on the mission, I want to stop doing this hill climb, because I am probably going to be discarding the results of the hill climb and aborting the mission anyway. So my loop becomes, until abort, find next neighbor. I could very well just say return data here. In fact, I'm going to do that. And if the next neighbor, if the best neighbor doesn't improve things, then return data. So I'm just going to go ahead and make that change. There. Hey, I got rid of a line of code. Awesome. As I keep looking up to my right, that's because I normally put the camera up to the right, and I'm looking for the camera, and the camera's actually top dead center now, so I can be looking at my code and looking at the camera, look at the code, look at the camera. Anyway, so here's my loop. Find the neighbor. If this doesn't improve things, return the original data, and if it did improve things, then set the data to the next data and go find its neighbor, and so on and so on and so on. He does the same thing. He finds the best neighbor, then says, until the next neighbor doesn't improve things, we set next data and we go get the next neighbor. Boom, boom, boom. So same loop, twisted around so that I don't repeat myself, so I applied dry, even though I think this code is probably not as clear, but the engineer in me insists on unifying those two calls, so my apologies. That leaves two things we are just waving our hands over right now. First of all is, given a vector, find all of its neighbors. We deferred that. And then, given a vector, decide on its fitness. Well, the fitness function is going to come from the caller, so we really are going to ignore that. So the next thing we need to do in our hill climb package is, what is our next neighbor function? Best neighbor. I do a little more commenting here because I am not copying my files onto the vessel that has limited storage. So that's one decision I made on my current playthrough, was that I was going to always have my archive connection because I wanted to focus more on writing code and how do I make the code work rather than the game challenge, which I admit is a lot of fun. I will be doing code that fits inside the spacecraft, and maybe not this save all the time, but in future saves where I'm just having fun playing the game, I do that. In past saves where I've done that in the past, where you take your code and you try to compress it. You say, oh, everything I want to do fits, but it's 1,000 bytes too long. You start trimming here, trimming there. Well, not doing that this time. So I've put in documentation blocks here. So best neighbor, you had a data, fitness function, step size, and it doesn't provide defaults for these because it's only called internally. Best neighbor is an internal function. Notice Kevin's only exporting seek, and I'm only exporting seek. We're also exporting version numbers. I don't think anybody uses those. In a large enough system, we would want to have each library appear as an object, and we'd be able to say, what version are you? Are you compatible with me? When I'm asking for the current hill climb, am I getting a hill climb that has all the features I want? You know, so you want the same major number. We're doing semver here, which means if you are making changes to a library that are incompatible, you bump the first one. So I say I need version 1 or version 2 or version 3 of the API. And if I need version 2, version 3 is not going to work because I break things. The second number increments as you add things. So if I need version 1.2, it means I need something that was added in 1.2. 1.3 should work just fine. I'm just not going to use things. So for full versioning of libraries, which I don't think anything we're doing in KOS at this point. Now remember, here we are on the cusp of starting to go to MUN. We're not doing anything big enough that we need to say we need old versions of the library and new versions of the library. When we get there, we will start to worry about how do I make sure I have older and newer versions of the library there. So if I have to keep 1.x for the highest x when I have 2 available, how do I semver that? How do I set up my library so they can hand me back version 1, version 1.x, version 2.x, version 3.x, and so on? The third number is bug fixes. So 1.2.5 has 1.2 APIs, and it's the 5th refactoring, bug fixing, whatever. And 1.2.6 may make something faster or may solve a bug. As long as you are not dependent upon the behavior of the library's bugs, you don't care whether it's 1.5.1 or 1.5.2 or 1.5.3 or 1.5.4. You may say, I need 1.5.3 or better because you depend on a bug fix that didn't get in until 1.5.3. Or you're presenting enough data that a optimization that went in 1.5.3 makes it a tractable problem. Anyway, so that's version. Where was I? We've done seek. Back to looking at next neighbor again. Next neighbor says, this is largely unmodified except for the formatting differences. We want to track the best neighbor and the best data. And I made one difference here. Best, the value I return is going to be the neighbor that has the highest fitness, which is a vector. And he initializes best to just a 0. This means that if you have no neighbors, what are you going to do? Well, in his code, every vector has neighbors. Because if you're passing in an empty vector, that's useless. You would never call HILLCLIMB with an empty vector. In my code, I came up against a problem when I applied this. I wanted to use HILLCLIMB in a scenario where my vectors were 6 or 7 or 8 long, but I wanted to lock the third one. I wanted to use a common code to evaluate the vector and allow a lock. So I could say, this third entry, don't change it. But that opened up the possibility that all the entries might be locked. We might have no neighbors. So my decision when I was refactoring through that section, I don't think I'd require this anymore, was that if I have no neighbors, return the original data. And that would cause HILLCLIMB to say, oh, my best neighbor is the same as me, so just I'm done because I can't improve. Other than that, we need basically look at all of my neighbors for each neighbor in the list of all neighbors, which we're going to build later. Evaluate the fitness for that neighbor. And if that fitness is better than the best fitness so far, then return. And actually, if the best is data, then best fitness is going to be the fitness of this. What I'm about to do is going to make it slower. Okay, so what we're going to say is initialize best, and then call the fitness function so we have, yeah. This won't break the logic above. It does slow us down because we are now going to call the fitness function on the starting node at the beginning of our best neighbor work. Okay. Now this may allow us to do some optimizations here because we now know that best neighbor is going to return the original data if there's no change. So we're going to be calling the fitness function several times on this, but it also means that I no longer need this infinite. I no longer need to have infinity. And the other thing I'm going to do is eliminate the default step size. I dislike manifest constants. So seek will always require a step size because that's going to be different for different problems. No default there. And best fitness will start off as the fitness function of the original vector. So we no longer need a designated initial value that's infinite. So we're getting rid of constants. Yay! And as I am editing this, I am risking having all of my existing missions now fail if I make an editing goof. But still, the logic is the same. For each neighbor in the list of neighbors, evaluate its fitness. If it's better than the best so far, then bump it and return best. And I may end up unifying seek and best neighbor at some point, because now I can say if I set best to neighbor, then we do want to potentially continue onward. And if I get through this loop without setting best to neighbor, then we're done. So we could unify seek and best neighbor at this point and eliminate some calls to fitness function. But it would also mean one function is doing more than one thing, and we're nesting further in. You're still talking to me, aren't you? Hold on while I calm down my co-pilot. Had to tell her that the world was still going okay. So there's best neighbor. Very simple. I'm taking a lot longer to explain this than is strictly necessary. Y'all probably got the concept in like 10 seconds. So this says, how do we generate the list of neighbors? I mean, this is real simple. We iterate through a list of neighbors. We pick the best one. Well, how do we generate the list of neighbors? Again, I've done very little. My personal style dictated a couple of changes here. Neighbors, we're going to we only call neighbors from one place, and it never passes in a result. But if it did pass in a result, we would append our neighbors to that list. So neighbors can either create a new list and return it, or can append to an existing list. Either way. I am going to keep it the way it is. I'm going to have a third parameter that is the place to put the results, and I'm going to default it to create a new one. Now, in some languages, there are gotchas here. For example, if I defaulted a parameter to a list, then all of the calls that use the default would get the same list. I think that's Rust that does that, but I'm not sure. In this case, all of the calls to neighbor, if I have a default on Rust, it will get a new list. So it evaluates this function each time at runtime during the call, rather than evaluating once during compile time or in the first call. So we have our list, we have our data, we have our step size. So the neighbors of a vector, and we're in a discrete space. Hill climb is hill climbing through a discrete input space, and it's discretized by the step size. So if I have a vector of 4 elements, and I have a step size, then the neighbors are, for each element, perturb that element positive and negative by step size. So for I in range of 0 through data length, if this is something I added, if the element of the vector is a scalar, then we do exactly what Kevin does. And if it's not a scalar, Kevin's code over here would fail. And here's what we do. We take the index I, indexes into the data vector. We then make 2 copies of our original vector, and one of them we increment that element by step size, and one of them we decrement that element by the step size. Now, if the original value in the data vector is not a scalar, this operation may not do what you expect. So for instance, if the vector element was a string and step size was the string x, I think this would bump the element by appending x. And if the element of the string is a vector and the step size is a vector, then it would do a vector addition, which is kind of cool, but probably not the most sane thing to do if you're hill climbing and your state vector is a vector. You probably want to add to all of the components. So I believe this is only well defined for scalar step sizes and scalar data elements. So what I'm going to do here is I'm going to say if the data is of type scalar, then we're going to construct the neighbors by saying, first, make a copy and call it increment, and bump increment sub I by step size and add that to the result list. So I have reordered his internals to do the decrement and the increment separately. And I have said only do it if it's a scalar. So if I pass in a data element that one of the elements is a list or a vector or a string, then neighbors will skip over it. So essentially that will be locking it. So whatever is in data will be passed along, will be copied to the increments. So if we have a vector, if data is a list of 5 things, and the third one is a string, then we will end up producing neighbors where all the other ones are perturbed, but that element is just that same string, or just that same vector, or just that same list. We can revisit that later and say, well, what if our data is a vector, or what if our data is a list? My goodness, somebody is being chatty today. So that does that. So now we have this function which generates our list of neighbors, and it returns it to best neighbor, which evaluates all those neighbors and says pick the one that's best. If it's if we have a neighbor that is better than our original, then return the best neighbor. So it's the best of the neighbors or us. And then we have seek, which pulls it all together. The engineer in me that wants to produce code that always works perfectly robustly loves this layout. The engineer in me that wants to make things as compact as possible says, oh, we could inline all this shit all the way up and end up with a seek function that inlines it all. And I am resisting going that direction. But if I were to compact this, I would end up with a seek function that did all those things together and did it all in one place, unified the seek logic with the best neighbor logic, because we know this termination condition is merely if we If this never fires, then we're done. So there are theoretical things you could do to make it better, but I am not going to modify it any further. There's our logic. And by doing this, now when we pass in a step size, we will take our vector and we will step around in its lattice, the lattice being defined as grid points every step size in every dimension of the vector. We will step through that as long as each step improves things, and we'll do that until we come up with the one whose fitness function returns the best value. My goodness, you are being very extra chatty today. Somebody does not want me to go on with this video. So what I'm going to do is I'm going to chop this here. This is 25 minutes I talked about hill climb. 25 minutes for a 50-line original source that fits on one screen, which I turned into 80 lines, which doesn't fit on one screen in this font size. That's how long you would spend doing a code review. I hope that this has made hill climb clear. I did say I was going to go over maneuver though, and if my copilot will be quiet, we can do that. I'm going to go ahead and do it. So, maneuver. The purpose of maneuver code is to run the next maneuver on the list. Now she wants to be picked up. Meow meow. She's more interested in maneuver, I guess. So, what is this? So maneuver exec, the way Kevin originally wrote it, basically says, if we skip over the protection logic, wait until it's time to burn, which we figure out by taking current seconds plus ETA in the node minus half the time we will spend doing the maneuver burn. And there are people out there that say we want to subtract another little bit of time from that, so we actually, when we get to start time, we have a little dead time that we can spend doing a countdown or something. See? She's fascinated by this. And we keep tracking maneuver time. And Kevin says, well, we're going to repeatedly set the throttle to however long is remaining. So take the current burn vector magnitude, which is the remaining dV, figure out how long our current configuration would spend burning the engines at full to satisfy that dV, and set our throttle to it. And if it's less than 1 second remaining, then we're going to decrease. So the dV for, when we get down to under a second, we're going to start ramping our throttle down. So we're not going to slam the throttle from full to 0 all at once. That would not allow us great precision. But by reducing our throttle as we get down to the end, this allows us to closer approximate what we want. So that's our throttle. Our steering, we're always going to be trying to point ourselves in the direction of the current burn vector. Now, as we do the burn, the node will update. What do you want? Let her see if she can figure out what she wants. So we're always going to be trying to burn in the direction where the burn vector says we have remaining thrust. Now, as we get down to the end, the burn vectors get smaller and smaller, and it'll become a very tiny vector which will spin around based on whatever our error is, because we never point exactly where we're supposed to. We can point close, but not there. So termination condition is we save off the original burn vector, and when the remaining burn, v dot of the remaining burn and V, when that's less than 0, so when we no longer have, when we have burned beyond that, when it's pointing, if our thrust is in this direction, when the remaining thrust is behind us, we're done. And he has some logic in here that says, while we're waiting, if the maximum thrust available from the ship is less than 0.1, we're going to stage, and if a tenth of a second after we stage, the maximum thrust is still less than 0.1, then we're going to stop. So he's got some auto staging logic in there. When we're done, set throttle to 0, unlock the steering, remove the node, and wait. So that's his logic. I have reordered his code, so let's go down to the exec functions again. First thing you'll notice is my code is slightly shorter because I have an auto stager over somewhere else running in the background. All of my missions are going to be using this auto stager, which sits in the background and says, hey, if activating the current, if staging would discard engines that are all burned out, okay, if I don't have any engines in the current stage, I can safely stage, it'll just get rid of engines that are burned out, then it's going to go ahead and do that. So somewhere else, someone else handles the staging. So my corresponding logic is same thing. We have some protection logic. We save off our original burn vector. Kevin is actually the first person I saw that use this idea of dot producting the original burn vector with the current burn vector to decide when it's time to ditch. Same computation for start time. And like him, I say if auto warp, then we're going to warp to the start time minus 30. So if this auto warp parameter is set, okay, so if you call maneuver exec, you can pass it a parameter that's optional. It says true, says to please warp to it. And if that's set, then we're going to warp to start time minus 30. And we are going to wait until time seconds is time. So whether we warp or not, we're going to hold here at this point in the code until it's time to fire. Same thing he does. And his lock basically locks the throttle to something that's a linear function of how much time is left. I'm doing the similar thing, but I'm taking the square root. So in his world, your throttle will start out at 1 and will drop fairly sharply and will have a long tail of being nearly 0. Because if you're close to 0 and there's not a lot of time left at full throttle, then we're staying at 0. So that's the behavior under this locking throttle to a linear function of the remaining magnitude. I did a little math, and it turns out that if I lock my throttle to the square root, that means that we don't drop quite as quickly. And in fact, with a square root, what happens is you'll see the throttle smoothly go from 1 to 0 at a constant rate. So you're changing the throttle at almost constant time. And that's because if we were to do it the other way, and I remember most physics is reversible, if you start a throttle from 0 and ramp it up linearly, then the amount of dV we have applied is proportional to the square of how much throttle we've applied, the square of the time. So coming back the other way, we want our throttle to ramp down proportional to the square root of the dV, or the square root of the maneuver time remaining. So I applied the square root. We still have a behavior that gets us extremely good precision on the burn, and the throttle down becomes a nice smooth linear throttle down rather than a ramp down and then slower. So we end up with almost as good precision and much faster execution. So that's my square root modification. And we do that as a lock. and we are going to use a wait until. We don't need to have any logic inside here. So this is until something do nothing. Well, that's it, just a wait until. And one other thing you see sprinkled around here. We support the abort. So if the abort switch is turned on, when we start, we just return. Warp 2, if we are in the middle of a warp, we're going to ignore the abort switch in the middle of the warp. So warp 2 does what warp 2 does. Except, I'm just recalling here, warp 2 might return immediately having set the warp up. So what we're really doing here when we do a warp 2 is we're not actually waiting for the warp 2 to complete. We're just turning it on, and we still wait here. So I've added or abort. So if somebody hits the abort switch, we're going to stop waiting. We're going to lock the throttle to some appropriate value or some inappropriate value briefly. Then once we've locked the throttle, we get to here and we say, well, if we're in the middle of the burn and somebody hits the abort, we're done burning. Lock the throttle to 0, unlock steering, remove the next node, and return. I use a wait 0 to basically let the physics system do one tick. I prefer to use wait 0 whenever I add a node, remove a node, or change the value of a node, which allows the physics system to do one tick to update the state of the node list, state of the vehicle, and so on. So, boom, there we go. Remove next node. We've got 0 throttle. We're releasing the steering. We're done. So there's maneuver exec. Both of these require a helper function, maneuver time. Maneuver time says give it a delta V, and assuming the ship is in its current state, compute how long the current ship with the current mass, current engines, current fuel load will take to apply that delta V from where we are now. Now I have split his function into 2 parts. So his function basically says we're going to do the math. Here's the value of G, and we're going to use, and the ship mass is in tons, and we're going to convert the ship mass into kilograms on his side. And E is a constant. So we go through and we look at all of our engines, and for all the engines that are ignited and not flamed out, we're going to count up the available thrust, and we're going to count up the ISP, and we're going to count the engines, and then we're going to set ISP to ISP divided by engine count. So his net ISP is the arithmetic average of the ISP of the engines. This is only correct if all of the engines have the same available thrust. So if all your engines are the same, if you've got 5 Yadas, then this gets you, add up all the ISPs and divide by the number of engines, and that comes back up with the engine ISP of the engine that you have replicated. Works perfectly if all of your engines are identical. Fails if some of your engines are, say, some solid rocket boosters that are still firing and some are liquid fuel engines. Fails if you happen to have a stage that has one higher ISP engine and then a bunch of smaller, lower ISP engines that are more gimbaled. The correct formula where your engines aren't the same is as follows. You look through the engines, and just as he did, find the ones that are ignited and not flamed out. Flame out is specifically if the engine has no fuel available. So if you have any fuel that's feeding this engine and you're ignited, then we're in here. What you add up is the available thrust from that engine. So if the engine is being thrust limited, we want to use the limited thrust. The available thrust divided by the advertised ISP of the engine. So that gets us a sum, and we're going to take that available thrust, that total sum, we're going to say the available thrust for the whole ship. Okay, we've added up all of the engines that are thrusting. So we say available thrust, this already gets added up for us, divided by this sum. So total force divided by the sum across all engines of the force of that engine divided by the ISP of the engine. That gets us ISP. And then we multiply by a conversion factor, which is set equal to the nominal gravity at the surface of Kerbin, or Earth. This is because the ISP rating of an engine does not depend on gravity. It depends on atmospheric pressure. So it's got a the engine has an ISP rating in vacuum, and it has an ISP rating in a pressure system, because if you're firing your engines into an atmosphere that has atmospheric pressure, your exhaust velocity is different. Different engines will have different impacts. But in no case does this need to be the actual gravity. So his computation of G here is unnecessary. Now he's actually computing it with the current body. So his formula would be incorrect if you were in orbit around Mun. Okay? So the ISP of the engine is computed relative to the gravity around Kerbin, always. So we use G0. G0 comes to us from constants. And it's literally a conversion factor. It's 9.8 meters per second. So we want to use 9.8 meters per second, multiplied by the ISP, which is in seconds. It's a rating of an engine. So that gives us a result, which is in meters per second, which is the aggregate exhaust velocity. So if we had just one engine, this would be the correct calculation for the exhaust velocity of the engine in vacuum. And I'm going to just throw out here the idea that if we're using maneuver nodes, we are probably placing those maneuver nodes in vacuum. I don't think I have ever planned a maneuver where a maneuver node was inside Kerbin's atmosphere. So this computation, if we were to place it inside the atmosphere, I would need to recover the ISP of the engine at the current pressure. So if we start doing that, calculating the exhaust velocity during this computation, we'll have to know what the maneuver node is during this computation to get the correct ISP of the engine for that altitude. And we would still then use G0. I suspect that when we start dealing with other planets, if we have maneuver nodes inside the atmospheres of those other planets, we'll have to be careful to continue to use G0 as the rating that was used for the engine and adjust the engine ISP for the atmospheric pressure that we're inside. So this gets us our proper VE. VE is, on Kevin's side, G times ISP. So if we were to modify his code, we would take this G times and move it over to ISP, collect G times ISP, and that's VE. So here's the new formula. Calculate VE, and then we do the same thing. So M is the ship mass. Okay, I have called it M0. He multiplies ship mass by 1,000, and he multiplies thrust by 1,000. Well, ship mass is on the top of the fraction, thrust is on the bottom. So the difference here is M is my mass in tons, 1,000 kilograms. F, original thrust, is in kilonewtons, and he multiplies that by 1,000 to put it into newtons. I keep it in kilonewtons here. So the units are different for M and F, but the ratio is the same. And actually, I should have written this differently. I should reorder the terms. So this is maneuver time is exhaust velocity times 1 minus e to the minus delta v over exhaust velocity. So take the change in velocity here, okay, divide that by our exhaust velocity. This is now a unitless number. So dv, ratio of dv to our exhaust velocity, e to that, subtract that from 1, multiply that by ve, and multiply that by mass divided by force. So velocity times mass divided by force. And the units all work out. Trust me on this. I've worked this math many, many times to make sure. And all we've done today is reorder some of the terms. So m0 over f, he multiplied both by 1,000. I didn't. Comes out to the same ratio. Multiply that by VE. Multiply that by this exponential term, which accounts for the fact that as you are burning your engines, the mass of the vehicle goes down. Oh, this is why that's on the left. So these two terms together represent the fact that the mass of the vehicle is decreasing as you burn. And the amount it decreases is this delta V divided by VE. There. That's actually my best formulation of maneuver time. So, calculate V sub E. In fact, if we are keeping the idea of support routines go below their callers, so now we have the main caller, maneuver exec, calls maneuver time, which calls V sub E. There we go. Now, what I have done differently in my version of the library is, first of all, I have exported these guys. So let's put the exports in order here. There we go. So what is this extra function at the top called step? This is a major refactoring. Kevin's maneuver library, when you call it, you call step, or you call exec. Exec maintains control and blocks until the maneuver is complete. This could be, in the case of a rendezvous like we've been doing, you could be in exec for hours while you're waiting to get to the start of the maneuver, and then you're in exec again for however long the maneuver takes to run. You're not returning control to your caller, which means your caller is up the creek. They can't do anything else. I want to use a paradigm in my code where I call in and say, look at the state of the system, take some action, and return. So maneuver step does this. Maneuver step is a single call that says adjust the state of the vessel to meet the needs of the next maneuver node. So maneuver step says protection, if abort, return 0, we're done. Maneuver step is going to return how long it wants me to wait before calling again. So 0 says we're done. If we don't have a maneuver node, we're done. If we are currently time warping, return 1. So if we're currently time warping, call me back in a second. If we're coming out of time warp but we haven't settled, call me back in a second. So this says if we ever get into time warp, maneuver step is just going to ignore the world. It's going to do nothing until we're back settled at warp, at base warp. So what do you do now? Find our next node. Well, we know we have a node because it's there. And look at our burn vector. Okay, so one of our decisions here is that we are going to stop when our actual burn vector opposes the direction of our original burn vector, when their dot product is negative. It doesn't have to oppose it completely, it just has to be swinging out wide. So we need to set this. So I'm saying if maneuver step time is 0, we're going to save our start time and we're going to save our S magnitude. Let's do those in the other order. I want to save our original burn vector direction. I just need the direction. So if step S is 0 magnitude vector, if it's set to 0, then we're going to set it to the normalized burn vector. We're also going to save off the start time of the maneuver, which is time in seconds plus ETA minus the maneuver time. So we're just going to compute this once. When do we want to start? This will give us a maneuver step T, which is our nominal time to start the burn. We're now going to create a local lambda that we can call or lock to, which will calculate our delta V in the direction of our original thrust vector. I'm trying to remind myself of how all of this works. Anyway, first thing we do with it is we say, if our current burn vector dotted with our saved burn vector is 0 or more negative. Now, if it's 0, what if I manage to absolutely 0 the burn vector? Well, I want that to terminate. So my termination condition includes the dot product being 0. Dot product is 0 or negative, we're done. So cut the throttle. We lock the steering to our current facing. So whatever direction we're pointing, I'm going to tell the control code, I'm going to tell KOS's cooked controls, just stop spinning us, just keep me facing the way I'm facing now. I'm going to remove the node that we've been executing because we are done. I'm going to clear out these two things, so I'm going to forget my step time and my direction and return 0 saying we're done. So there's our termination condition, and I can fold that because we're done with it. Calc dv, again, is the dot product of the step direction, the maneuver step direction. MNV step is me, so the S vector that I'm keeping, this calculates our delta V in the original direction. I'm going to fold that because we've looked at it and we're done looking at it. So steering setting. What's our steering setting? Well, I want to point my nose in the direction of the burn. I want to burn in a particular direction. Let's point the nose in that direction. And that's a vector. And an orientation requires one more thing, which is our roll. So we've got a vector pointing this direction. Which direction do we want our top vector? Let's use lookter up with facing top vector. So whatever direction the pilot's head is pointing, we're going to keep that as close as possible to that direction. That locks our steering so we don't just roll all over the place. Next thing is, what is our throttle setting? And I'm going to use something that I can lock to so that we can have our throttle and our steering be computed every physics cycle without calling this function every physics cycle. We don't need to reevaluate all this crap every physics cycle. But we do need to reevaluate our steering direction and our thrust quantity. So what's our thrust quantity? Well, first of all, let's take our step time minus time seconds. So how long do we have until it's time to burn? If we are before that, so if wait time is greater than 0, return 0. Do we use WT for anything else? Yeah, we do. If we recalculate it down here, we only use it once here, so this could equally be more clearly if time seconds is less than maneuver step T. That's a lot cleaner than using WT, which we don't use elsewhere in this computation. So if it's not yet time to burn, then our throttle is 0. So we're going to lock throttle to TH. It's going to return 0 until the appropriate time. So now we calculate our desired delta V. Wow, if delta V is less than 0, return 0. So if our termination condition is met, we're going to check this inside the lock. Because remember, we check the termination condition when we called the function. This lock is going to get called every physics tick after the function returns. And the moment our termination condition is set, we want our throttle to go to 0 immediately, even before the next call and maneuver step. So there it is. If the dot product is not positive, we're done. Okay, so now we take that dV value that we computed, and we're going to pass it into maneuver time. And we're saying, okay, how long would we have to burn the engines at full throttle to match this dV? Okay, there's our dt. And if that's at least 1 second, we don't need to do anything else. We're done with that. We can say, okay, if our remaining time at full throttle is a second or more, return 1. So full throttle. Boom. Get down to here, we say, well, we only have enough dV left for half a second at full throttle. Okay, so we're going to set the throttle to the square root of that. So again, that square root is what I said about that curve. So that our throttle is going to come down nice and smoothly because it is the square root of how long we would normally have if we had full throttle. That closed brace is the end of this delegate. So this is all a function delegate from here to here. It's a function delegate we are going to execute over and over and over again, and we're going to lock the throttle to it. The reason why I used a function delegate instead of writing an expression is I wasn't sure I could write an expression cleanly that expressed this conditional logic if this returns 0, if this returns 0, if this return 1, return that. I could have written a big long ternary. So I could have used a ternary choose to say choose 0 if this, else choose 0 if that, else choose 1 if that. And then how do you get the dV? It was cleaner just to write the code linearly, have it return the value, and then lock the throttle to the result of calling that delegate. So we've locked our steering, we've locked our throttle. Now we need to decide how long we want to wait before the next call to this script. Okay, so wait time. We computed wait time up above, and then we decided not to compute it again. We have our starting time, which we calculated once. I want to minimize the number of times we call maneuver time, and then I realized I couldn't. So we literally have to recompute the maneuver time each time through because it may be changing, and I want it to be exact. We could store the end of the maneuver and just assume the end of the maneuver isn't going to change. It depends on how much confidence you have. We could easily do that. In fact, yes, I'm going to do that. If 0 equals maneuver step, I'm going to use E for elapsed time. I'm going to assume that maneuver time of Vmag is going to be consistent for the rest of the time. What I mean by that is that the ending time of the maneuver will be consistent. It's the ending time of the maneuver. Okay, I have a whole bunch of things here, and rather than have it, so it's a local MNV step active is false. Things we need to keep are the starting time and the ending time and the direction. Let's fix those. So now we're going to have a flag that says whether these are set or not, the direction we're burning, or the direction of the original burn. Now, it's possible to have the maneuver step always fire in that direction rather than fire in a corrected direction. We could just lock ourselves to the original direction and we actually get fairly good precision. But by locking ourselves to the delta V here, we get better precision. So start time and final time. So now we're going to say if not MNV step active, then we're going to do a bunch of things, including set. So what are our computations? First of all, set MNV step dir to V colon mag, V colon normalized. Set MNV local MNV, let's call this DT, is MNV time of V colon mag, I think, yes. Look, and then set MNV step start T to time seconds plus N ETA plus DT over 2 MNV step final T to okay. So with that set, okay, I am screwing the pooch here. Sorry for the language. Because, yes, the ending time is not going to be constant. We do need to call it here because DV is going to be getting smaller and smaller. Okay, so we go back to here and I look at maneuver.ks like that. And I have made a bunch of changes here while we've been sitting here talking that I should not have made. And the most important ones are I should not have modified anything in maneuver step. Did I say something about over-engineering things from time to time? Yes, I did. So I may have simplified things while we were talking. This is why I use source code control systems, because those changes I made were entirely out of line. I must calculate maneuver time here, because as we ramp our throttle down, the actual time at which we will stop is going to change. It will tend to ramp out. So, rewinding. Maneuver step says all sorts of termination conditions we won't want to do something. We save off our initial state, which is the time at which we will start the burn, and the original direction. We have a delegate for calculating our remaining delta V. We have our termination condition, which says, okay, we're going to be calling maneuver step periodically, and this isn't going to fire the instant we're done, but it will fire the next call. That's termination. Then we set our steering to, oh, okay, so this version, in fact, does lock our steering to the original burn vector direction, so we are not going to be slewing our vehicle around to correct. I'm not going to fix that because we already saw what happens when Greg starts fixing code. Then we have this throttle computation. I am not going to fix it because we saw what happens when Greg starts fixing code. So that locks our throttle and our steering, and then we say, how long do you want to wait before the next time we call? Figure our time until the start. If it is within a couple of seconds, so if we have 1.5 seconds left before we start, I want to return that time. So we will try to call the function back at exactly the start time. This is less important now that I have this ramp up the throttle logic here. If we've got more than 60 seconds to wait, we're going to initiate a warp 2. And the moment we do that, we'll end up getting these guys triggering up here. And if it's different from that, if we're not either a long time or a very short time, we're just going to wait a second. So that gets me a maneuver step that I call it does something and returns. And it implements roughly the same logic as the original code. And this is the maneuver step we are actually using, I believe. Let me check. I actually have KS programming loaded up in my workspace here so I can refer to it as necessary. So our test flight is go.ks here in Meaningfully Hosted Pickle. And when we want to do this, you notice that for my mission plan, the exec transfer and exec correct steps that we worked on in the previous video, just call this maneuver step over and over again. And when we flew it, we saw how quickly that worked. So with that in mind, knowing that it works, and it works fast, and it works efficiently, this is my diff listing. What have I changed since the last time it worked? Well, I moved this maneuver down. I reordered this. I think my best bet at this point is to not use these changes. So I'm going to go back to here. Oh, I didn't know I had Farkos open. Ah, okay. Farkos is a different image of this. So HILLCLIMB. In fact, I think what I'm going to do. Oh, I didn't check in my support for abort in HILLCLIMB. Oh. Oh my. Oh my. I need to check this in. But I need to not check this in. So this guy gets reverted. Let's rate this right now. HILLCLIMB tweaks. Add document support for abort and other edits. And then behavioral, eliminate infinity and default step size. Best neighbor returns original if no neighbors are better. That's how we eliminate the infinity sentinel value. Don't like sentinel values, really don't. In-band signaling is weak. Okay, so that's got that. So we stage HILLCLIMB and commit. So, oh, it's got all of the projects that I have recently looked at. Yeah, fine. And meaningfully holistic pickle. What mods did we get here? I did some things to T0. Actually, yes, I eliminated Prev T0. You know what? I'm going to run a test of the pickle before I commit this script back again, just to make sure that what I did was working. Anyway, so that's hill climb and maneuver all done. Let me work this back to just hill climb and maneuver. And we're going to call that a video. I'm going to go make sure that the remaining changes to the pickle are good and get that committed and push it all back up to GitHub. And we'll talk to you all later.